Okay, let's go ahead and get started. Hello, everyone. I'm Charlie Smith, Executive Director of ESIG. I also serve in a leadership role with the Global Power System Transformation Consortium, or GPST, whose mission is to bring together key actors across the globe to catalyze a rapid, clean energy transition at unprecedented scale and speed. This is being done by providing a coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across the 5 action pillars. The foundation of the GPST is a group of 6 system operators from around the globe who are facing higher penetration of wind and solar inverter-based resources sooner than any other operators in the world. The 5 pillars of the consortium include research and peer learning, technical support, workforce development, technology adoption support and standardization, and open data and tools. ESIG is the lead on Pillar 1, and more information on GPST can be found at globalpst.org. As the lead on Pillar 1, ESIG would like to welcome you to the December monthly webinar of our joint GPST Pillar 1 ESIG webinar series. This series is in addition to the regular ESIG monthly webinar series and focuses on the GPST research agenda and associated topics being addressed in Pillar 1. Topics are presented by both the founding system operators and other advanced system operators active in Pillar 1, as well as members of industry and the research community participating in the GPST. An additional series of webinars on the other 4 pillars of the GPST is also being provided on a monthly basis through NREL. For those of you who would like to learn more about the GPST and how to engage, please go to globalpst.org and click on the Get Involved tab. Further information on ESIG can be found at esig.energy. Next, I would like to go over a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we will use the Slido platform at slido.com. To ask a question, please navigate to slido.com and enter ESIG19 as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions on Slido to allow you to cast a vote to help prioritize the questions submitted. We plan to save about 10 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Today's topic is on developing an EMT study and analysis environment for a 100% inverter-based power system. For all of you following this area, you know that this is a challenge we are all facing around the world. There's a lot of attention being paid to this particular challenge, and nowhere more so than at Energinet in Denmark. This webinar explores the challenges associated with operating a 100% IBR-based power system with a focus on the use of simulation support for decision-making. The webinar will also share insights into the process and methodology behind developing a system-level EMT study and analysis environment. It will be presented by Kwon, a senior power systems engineer at Energinet, with a background in power electronics and more than 10 years of experience in the industry. Jun has technical lead and support responsibilities on multiple cross-cutting projects, including the Bornholm Energy Island and the North Sea Wind Power Hub. He leads strategic grid-forming technology roadmapping activities and development of EMT system-level simulations at Energinet. I greatly value Jun's leadership and contributions to the industry and the energy transformation, and I look forward to hearing what he has to say. Okay, just a short reminder once again to use Slido at slido.com with the event code of ESIG19 to ask your questions. Let's go ahead and get started. Jun, I will now turn it over to you.
Thank you, Charles, for introducing me, and thanks for our participants joining this webinar today. Let me share my screen just a moment. So you can see my screen, right? Yes, thanks again. I'm very happy to be here from the Energinet as a represent to share our experience on the developing on the EMT studies and analysis environment for 100% inverter-based power systems. I will address different topics today webinar, so visions, our view on the different principles regarding the stabilities and challenges. What is the main challenges we see as a three categories? And based on that initiative, we have started our development process for system level EMT study environment in the Danish power system. So I would like to introduce more deep insight of our process and what is achievement so far. And of course, there are still some many challenges we have to address in the coming years. And would like to introduce what is the future application from the Danish context. So let me introduce the Energinet, who we are. So maybe some of the participants know us, but maybe some of them don't know us. So Energinet is responsible for ensuring that the Denmark is supplied with gas and electricity, so both today and in the year to come. So we are the TSO, transmission system operator companies, and have two companies in the main companies, the transmission operator and the system operators. So we were established to safeguard the interest of the society, and our aim is to create a value for the people and the business in Denmark. So the money we earn is not for the company, but to guarantee the efficient operations and the development of the electricity and gas supplies for the benefits of the society as a whole. And we move toward the 100% green energy system as our great vision and goals. So we are an independent public enterprise owned by the Danish Ministry of the Climate and the Energy and the Utilities. And we have two different offices in Denmark. One is in the Fredericia, and another one is in the near the Copenhagen area. And we are now around 2,000 to 2,500 employees working for electricity and the gas business. Before I go jump into the very details of how we have developed the EMT system level environment in the Danish power systems, I'd like to share our visions on the stabilities. So as Energinet is aiming to integrate more renewable energy and the power electronics based systems by 2030, or almost 100% inverter power electronics power based systems. So our journey to develop new tools and environment begins with these visions that I would like to share here. We're finding a solution for the most suitable technologies, which ensure cost-effective system stability, is upcoming challenges to the Danish power system to create a green power system in Denmark. So in that context, we stand by for steadfast principles. So principle one is that the predict and mitigate. So imagine the world where we can predict and mitigate any instability issues and the critical system events. So our aim is to operate the systems without unnecessary cautions, yet ensuring the robustness. And the principle two is that the solution in the harmonies. So here we aim is not just to address instability, but to embrace it with a right mix of the constructions, operational strategies, and market solutions. So simply a symphony of ideas and fostering the stabilities. And the principle three is the technological masteries. So I would say so. Our the missions is to us to embrace the cutting edge technologies. So our tool to resolve the challenges of the tomorrow and to ensure stable and resilient power systems. And the last principle from our perspective is the communication empowerment. So communication is our sort of the lighthouse. So we have put quite an effort for the last several years to share our complexity of the stability challenges so that everyone can partake in the understandings and the debating with us and the contributing to the crafting the viable solutions. So we as Energinet point of view, we can categorize the stability challenges for three different ways. Since an unmanaged system stability will lead to a number of the challenges. So system stability sounds like a very simple word, but it will involve many different aspects. So the first one is the critical system events. So imagine that some of the scenario where the unforeseen strikes or some sudden unplanned outages can happen, and the more production or consumption plants can reduce the powers. This actually derive the system causing some local congestions and imbalances or decouplings. So plant damage become also somehow the grim realities. And the second, the stability challenges in the Danish power systems is that the preventive limitations and the down regulations. So in our second categories, different challenges emerges. So I needed to address the stability concerns by down-regulating and the productions or consumptions, or imposing the limitation on the foreign capacity. Since the Danish power system is interconnected with many different the neighboring countries, so these actions through the preventive often leads to the economical unfavorable operations within the power systems. And the third one is the unforeseen delay and the cost. So our final category expands as challenges surface late in the project phase during the compliance testing or initial operations or the commissioning stages, and so on. So any challenges discovered late in the project phase would derive unfortunate delay, and it will ballooning the costs and impeding the project progress. So as we face these challenges, we need to think about their important effects, and it's very important to use both good technology and the tool development and the smart planning to deal with these difficulty situations. So as introduced in our visions and the main three challenges in regards to the stabilities. So stability management is a really pivotal challenges in the Danish power system, especially we need to think about the holistic approaches where various aspects should be considered to handle stability in a system level, also considering some costs coming following together. So So for example, let me use some laser pointer here. So in the power system, so for example, whenever we need to integrate the wind and the PV power plants, we need to think about the grid code compliance and the simulation model and the delivery and the validations, where all the input is coming from the system and the plant level analysis, and also technical requirement, network code is one of the reference that all the developer has to follow, and that stability issues also in relations with the market things and any aspects we observed in the real-time system level surveillance and the control is also correlated with many other aspects. So basically, our contributions to this development of the EMT system level simulations is to increase our accuracies and to provide the precise simulation result, which can contribute to our decision-making systems. So this development of the EMT tools doesn't mean that we can 100% assure all the stability in the Danish power systems, but this is one step forward to contribute to our decision making and to secure our stability in the Danish power systems. So Energinet has been working on the RMS-based stability state assessment since 2009 or something, the quite old time, and to support the decision making from the operation department and evaluate the future risk of the instability for coming revision plans and the critical maintenance scenario in the Danish power system. So the process of how to set up system level simulation was to set up the worst case of the power flow scenario, considering our historical data of the power flow, for example, and the tendency of the import and the export of the power from the HVCs and the renewable energies, production levels depending on the weather conditions, also considering system condition, constraint and the system operation guideline between the neighboring countries. So we make such a very worst cases setup, considering some realistic situations, and then we apply the different fault events and the disturbance based on our historical experience and engineering judgment to potential locations to evaluate the entire voltage active and reactive power performance according to the predefined criterions. However, the overall performance of the dynamic behavior observed in the RMS-based simulations was quite unsure in some of the recent study cases, considering more power electronics devices to be integrated. So RMS tool is a very good tools. It doesn't mean, I mean, our development of the 100%, our development of the EMT system level simulation doesn't mean that we don't use the RMS. We need still quite a strong support to set up the load flow and scenario setup. We need RMS environment and this line between the initializations and offline the fault and considering different event, that might be the boundary to think about the possibility to execute the system level EMT analysis. So there has been several cases why we start to think about the system level EMT simulations. And the first case is was some of the oscillation situation in real life in the Danish power systems. So for your better understandings, in the Denmark, even though we are a very small country, we have a very special setup in the Danish power systems. We call that DK1 and the DK2. So DK1 is the one of the network we have where they are synchronized with the European countries. So basically connected to Germany through the AC cables and interconnected through HVCs to different countries, Netherlands and England and then Norway and Sweden and so on. And we have one more systems called DK2, which is in the eastern part of the Denmark, where they are synchronized with the Nordic country. So in between DK1 and DK2, we have one HVC systems to synchronize to different signals area. So some of the oscillation issues recently happened in this area. We call that end-drop stations. The issues is that we have observed oscillations around the 2 to 3 hertz, and the oscillation magnitude was depending on the power flow. We were able to observe around the 5 to 10 megawatt plus minus oscillations could be observed. And that happens time to time, meaning that depending on the operation coming from the different power electronics devices like wind power plants and the other the devices, we will time to time observe that oscillations. And our biggest concern is that it is not only due to one of the HVCs in the operation in these stations, which is called Cobra cables. That was this interaction issues is more likely caused by the interactions between these HVCs and also other wind power plants. We call that Hans level 1 to 3. It's a quite a big challenge is how to make the best tuning to avoid these issues, since we are not really able to share and exchange the models. And another issue is that we were not really able to observe such kind of oscillations issues in our RMS environment. And another concerns we are looking into is that there are more power electronics systems is coming to be integrated into this West Coast area, and also one of the big longest sea cables connected HV system to UK is one station away from the Discover cables. So if there are more power electronics to be integrated in this area, it'll be very difficult, and the challenges to handle such kind of oscillations and coordinating the outer loop control of the different power electronic systems. So to address and resolve such a kind of issues, we have experienced that the EMT environment and the specific models considering the real code is almost the necessary conditions to address such an issues. And another case is we have also experienced, I think that this case has been shared in some different webinars, where this is a DK2 cases. So meaning that this DK2 system is synchronized with northern countries, and this messy the grid, this area is the Copenhagen area, where our capital is located in this area. And as you can see that the western and the eastern part of this island, we call the Shetland, is actually 400 kV rise. In the 400 kV line wise is connected through these two lines, and through some of the fire and some fault happened in this area. It happened around 3 years ago from now, that we lost basically those two backbone 400 kV lines between the western and the eastern part. And what happens from there is that the situations at the moment in real life was that it was summer seasons, and as mentioned, the Shetland is actually they connected through the one HVC called Storbelt, and another HVC, LCC HVC, is connected to Germany. And this entire DK2 power system was actually getting all the power imported through these two HVCs, and no really power exchanges with the Sweden's. So meaning that all the consumption in the DK2 power systems was basically covered by these two HVCs and some amount of the renewable energy coming from the wind and the PV, but it was not that much. So once that the incident happens, which decouple the western and eastern part of the Shetland, actually we experience such a multiple sequential events, quite complicated to explain all the details, but basically we have experienced multiple commutation failure, and it derived the trip of the Storbelt HVCs and the synchronous condenser in the Białystok stations, and at the end it also tripped the contact HVCs. So it was a very critical situation at the moment, and also this power support coming from the Sweden was not able to support through these AC cables. Then actually that was a very risky situation that the Copenhagen area could also experience some of the blackout. Another issues why this case is quite important for us is that we typically do quite a lot of revision studies for supporting the operations and the decision making, and also to see how the line outages for the maintenance can derive some critical situations. But we were not really able to estimate and see such kind of critical cases in an RMS environment. The main reason was that the vendor-specific model was not able to capture such multiple sequential events precisely, and also some of the details of the modelings in the protection and trip sequence in the RMS dynamic models was not good enough to represent such event cases. So basically, we have made some comparison by involving some measurement from the stations, and created the same cases using the system level EMT simulations, and also in the RMS environment what we have. So you can exactly some differences. Of course, RMS environment was able to show some commutation failure, but the starting point of the oscillations and oscillation frequencies and some sequential events caused by the multiple devices were not able to really be captured in the RMS environment. While the EMT environment, it was easily to capture such an events by applying the same type of the fault that we have observed in the real life. So, based on such stories and incident cases we have experienced, so we started to think about the development of the system level EMT simulation environment in the Energinet. So since the 2013, Energinet has received all the vendor-specific EMT models, and they have been used typically to validate RMS dynamic performance, since RMS-based system-level evaluation were the main tool in Energinet. However, sorry, based on the several observations in the real measurement and the study cases like introduced in the previous slides, EMT system-level simulation is also highly needed to specific study cases so far. But see that the demand will become higher as there are more IBR inverter-based resources to be integrated to the Danish power system. So main key challenges were actually the data conversion process from the one tool to another tools. There are some references you might have seen and read some report from other TSOs. So PSSE is one of the RMS, the phasor domain tools typically used in the USA and Australian market. But the Power Factory, which is quite a common tools in the European market, was not really integrated in this PSCAT, which is a main EMT tool in the Energinet. So it was quite a big challenges for us how to really convert all the data coming from the power factories, and or how to manage the databases and how to handle those such kind of data to really enable the system level EMT simulations. There were quite many challenges. On the top of that data conversion process, there has been also several challenges how to integrate the vendor-specific models and so on. So we started these activities regarding the development of the EMT system level simulations since 2020 January. And all the activities has done so far until now, 2023 December, is that the validation of the vendor models since 2013, as mentioned, and also data mapping process and model initialization process. We have developed that together with our co-partners, the Manitoba Hydro International and the PSCAT. And based on that such a process, we have now the two different network models. One is a DK1 EMT network models, and another one is a DK2 EMT network model, since we have two different synchronous area. Of course, we can connect them through the HVC vendor-specific model, but now our setup is to have two different DK1 and DK2 system network models. And it is also necessary to develop some user-defined model and functions for the Danish context to support our system level EMT models. And also there are quite many the pre and post processing for the system EMT model preparations. For example, initializations and the reduction of the models from the Power Factory, since the Power Factory is a database based the tools where they are actually handling quite a lot of data which are not necessary in some points. So unnecessary data should be deleted, for examples, and handling such a kind of a very small and detailed issues require quite a lot of scripting issues. But we were really able to handle that based on the good collaboration with PSCAT MHI. And from we need actually more cases actually to improve the qualities and validate our EMT system level simulations environment so far we have developed. So we need to involve the more models to more project. So daily grid connection process in good collaboration with our grid connection teams. So basically, whenever there is a new grid connections, PV, wind, and something else is to be connected in the transmission lines, then so far we typically validate their performance using the Tevron source, but we are thinking to integrate and validate their performance in the system level simulations depending on the area and the size of the plants. And we are also thinking to look at some future technology, the deployment in the Danish power systems, for example, grid farming. We have involved quite a lot of vendors and the developers based on the market dialogues, and we are in the stages to integrate and evaluate the different grid farming functionality and the technology coming from the different technologies in the Danish power system to see what is the really available functionality and the technical readiness level ready to be the part of the Danish power systems. So such a project will be more involved to validate and improve the Danish power systems EMT environment. And the model improvement and the validation is also very necessary process. So we need to debugging and some improved robustness and the more user-friendly EMT data management to improve the system level study features is somehow the necessary items that we have to put more resources in the coming years. Since the time is running out, I can quickly introduce some of the process here. So EMT process, as mentioned, the Energinet is using the Power Factory models. So basically, you can imagine that once all the balance and the load flow scenario, power flow is ready from the Power Factory, then we make that as a full model, meaning that all the DSO and some details, multiple bus bar system is implemented in the Power Factory. But depending on the cases where for now we don't consider the multiple bus bar system, so we use some of the script to reduce the model before we integrate that to the PSCAP. So once the model is ready from the Power Factory, then we export that to XML file, actually DGS data supported by the Power Factory. And that will be imported to the PRSIM, one of some extra tools developed by the MHIs, where it was really well able to support all the data format from the PSSE, but there has been several challenges to really integrate the PSSE data as well. So because it was not really able to handle the multiple different load flow scenario coming from the same topologies. So actually we tackled that challenges together with MHI, and now we can handle some multiple different scenario coming from the topologies using some new setup in the PRSIMs. So once PRSIM is able to import some new XML file depending on the scenario, then it will be exported to the PSCAP, and we have some internal process for load flow checking. So basically, we need to check the quality of the PSCAD EMT system level model exported from the PRSIMs to check if they have a quite a good balance compared to power factory load flow. So for example, voltage and the active power, reactive power, we do such kind of quality check. And then we do some final check with the vendor models. And it is quite a challenges actually at the beginning, how to really accelerate the simulation time, since it was quite well-known challenges for system level EMT simulations. People typically think that it takes quite a long time to run the system level EMT simulations. But now actually all the hardware and parallel computing technologies has been quite well matured now. So actually we also use the same features to really enable this system level EMT simulations. So basically we split the network, our Danish power systems, to several subnet, and integrated a multiple number of the vendor specific models in parallel. That is the some level of the EMT model is ready to execute some simulations. So by applying all the multiple disturbances and the fault events based on our engineering judgment and experience, we run several scripts to execute the simulations and derive and collect all the results for the analysis. So this is somehow the example that I can share. So on the left side, this is a DK2 system level EMT models, where you can see the entire network in the transmission levels on this side. But it is quite a challenges to run with the entire network, depending on actually time step and the size of the network. But based on some of the tests, we decided to split that to several number of the subtasks sub-network. So far, the current setup we are using is that for DK1, we have 4 to 5 subnet, and around 40 vendor models are connected in and running in parallel. So total PNI simulation is around 45 PNI for DK1, and for DK2 around 47 to 57 PNI, depending on the year of the scenario. So in total, we can run DK1, DK2 simulations for 10 seconds in the simulation time. We can run it in a 16 minute and 15 minute or 17 minute around that time. And we are currently using the Azure-based the simulation servers, and that setup really able to support all the parallel networking. And actually, we are quite satisfied with this performance so far. So some of the examples that we have observed, which were not observed in the RMS system level studies, is basically more interaction and oscillation issues. So for example, some oscillations at the active power around the 300 Hertz and 6 Hertz around the voltages, depending on the scenario and the configuration and the load flow scenario, we could really be able to observe that such oscillations, which is coming from the interactions between the power electronics devices and some interaction between the power electronics to the grid and so on. So the handling and observing such oscillations were quite different aspects compared to the RMS-based studies. So we see that the handle such kind of issues that I introduced in the one of the example coming from the west coast of the DK1. This system level EMT simulation is quite necessary to handle such interaction issues, especially in some of the area where the or many power electronics are integrated. And on the top of the time domain simulations, we are on the development of the extra tool in parallel to support more detailed analysis and overview of the system dynamics. So, for example, small signal toolboxes, impedance measurement will also be integrated in the futures to measure the different impedance from the different vendor model, seen from the point of connections, and analyze the interaction point between the converter and the network or converter to converters. So where some example, you can see that some 300 Hertz oscillations we have observed in the time domain. We can see some impedance interactions through the impedance network scanning by perturbing the system and the specific models and towards the network. So of course, these features we need a little bit more effort to really make it matured. But we are on the development to support our system level EMT simulations and to figure out what is the main root cause of the such oscillation or instability issues in a small signal stability wise. So this is my last slide. So typically, a known challenge in the EMT simulation, especially system level EMT simulation, was the simulation time. But as mentioned, it is known as a simulation takes longer than the RMS once people integrate more than the specific model, but which is not anymore the barrier, in my opinion, to enable the system level EMT simulations. Since that is quite covered and supported by many parallel computing network, so the running the system level simulations is not really anymore the challenges due to simulation time, but there are some several practical challenges that I would like to address and share with you. So systematical model and the data management in the EMT environment. It was quite a successful development and achievement so far, but we need to put a little bit more effort for the model deployment. For example, system level protections and the disturbance components. For example, all the TSOs has also in a high level context, there are system level protection and the system secure functions coming, for example, which is connected to the multiple HVCs and the power plants or line disconnection and the connection in some of the area, depending on the instability issues. So such a kind of the system level functions automatically integrating for a quick simulation setup is still quite a challenges. And another challenge is known is that the compiler compatibility issues with the parallel computations. So for example, we have received all the vendor-specific EMT models since 2013. So some of them is running with quite old Visual Studio and Interfortran. Some of the newest version of the vendor-specific model in the latest power plant project, they are running with some latest version of the Visual Studio and the Interfortran. And to run them together, so we need quite a technical support from the software developers, and it takes quite a time to really resolve such kind of issues. And also we really run this system level simulations in the EMTs. We could see that there are quite a lot of big data is coming, several gigawatts, depending on how many data you would like to measure it, and also different depending on the time steps you would like to point out. So data acquisition and post-processing of such a large big data and their visualizations for system overview, for example, like RMS tools, is still quite challenges. We have developed some internal visualization tools and some screening result based on the EMT time domain simulations, but some standard and official tools supported by the software might be really necessary. And the update grid connection model requirement considering extra needs from the system level EMT simulations, which means that actually we have put our model requirement in connection with the grid connection model requirement. We typically mention the compiler versions and the PSCAD versions, and that model should be able to comply with all our grid connection requirement. But if really you would like to enable some features like a system EMT level based validations in connection with the grid connection process, then actually we need to define several extra effort. For example, 10-second simulation in the EMT should be done in, for example, 1 minute. So such a kind of a special requirement and investigation is necessary to really enable these system level simulations. So the future and the current applications from our perspective is that we will integrate these system level simulations as a part of our grid connection cases. And we have quite many Energy Island projects, Bornholm Energy Island and the North Wind Power Hub. And their impact to our Danish power system is quite huge. So we see that the high needs of system level EMT simulations to integrate such a big energy island to see correct interaction and the dynamic behavior and how they affect to our systems. And as mentioned, the deployment of the future technologies, we have already quite 11 companies to be involved at this deployment of the grid forming project in the Energinet. So we will try to leverage and utilize our environment so far developed. So we will be able to observe some better, precise, accurate the interaction between the grid forming and the following than what we have observed in RMS. So that is somehow the expectations. And the revision studies and for some of the critical scenario we have done for so far in the RMS environment, but depending on the region and some critical scenario, for example, very weak grid or weak grid, we will try to use this system level EMT environment to support revision studies and for making decisions like I mentioned in the beginning. And the validation and analysis of the real events, which is very important actually to really increase the quality of the simulation environment. We have done so far many times in the RMS, but there are always has been several gaps. But for EMTs, we will try to involve a more system level event like a fault or any trip of the lines or HVCs. Depending on the severeness of the cases, we will try to involve them by directly importing the SCADA data to RMS and the RMS conversions to the EMT and validate and improve the quality of the models. And integrate more extra tools like introduce the state space and impedance scan tools in parallel to support the EMT development. System level EMT tools is one of the big challenges and the coming activities in the Energinet. So the last but not least, this is somehow the acknowledgement. We Energinet, there are around 7-8 people working together to support and develop such features addressed here. And there was also quite great support from the MHI teams to support our initiative and to enable all the data conversion process. So that's all. And thank you for listening my presentation, and we can talk about any questions if you have.
Okay, Shun, thank you very much. That was a nice walk through what you're doing there at Energinet. So we're going to go ahead and move to the Slido and get the Slido questions up. Let's see. So one of them has kind of risen to the top much above the others. Actually, I think it's one that's of interest to everyone. What are the root causes and mitigation actions for the 2 to 3 hertz low frequency oscillations? Is the positive sequence model able to capture the issue?
I think you are mentioning about this first oscillation issues we have. I have mentioned.
Yes, I think so.
Actually, we didn't put so much effort in the frequency domain to figure out if that is due to some positive sequence or negative sequence interactions. We try to investigate the reason more in the time domain. But if I can share some details, then actually the main cause was due to some outer loop controller, which are interacting with other outer loop controller coming from the other power electronics. But that is not actually 100% sure, since the other model is, for example, wind farm in the host level 1 to 3 is not shareable to Cobra cables, as we have observed that oscillation in that station called N-drop. And it is actually quite a challenge so far. So we were not able to figure out very clearly what is the root cause of that one, and that is actually one of the challenges that we need to address in the system level EMT simulations.
More work to do.
Yes, exactly.
Yeah. Okay. What is the time step for the EMT simulation, and how do you handle vendor DLL models compiled for different time steps?
Actually, that is a very good questions. Actually, one of the good things, as I mentioned at the very beginning, we have Energinet received all the vendor model since 2013, and from that time, actually, we require very specific the time step 10 microseconds. So time step wasn't actually not really big issues. Some of the older models actually are running with some higher time step, but based on some help and the support in collaboration with the MHI, the different time step and the validation of the dynamic performance were really able to support to enable running all the models in parallel with 10 microseconds. So 10 microseconds is the fixed time step we are we are not currently using. And the compatibility issues is actually quite big issues. And again, we got quite a big support from the software companies since Interfortran compiler, Visual Studio compilers. That really depends on the environment coming from the vendors, OEM, who deliver the models. Of course, we can put that specific requirement as a part of our model requirement, but since the software environment also evolving, we can always require that very specific version. Based on that, some input and our experience, I believe that the software company, for example, PSCAD, is really aware of that issues, and that they are trying to make a new environment which allows user to put a different software compiler depending to the individual project, I mean, and running that together in parallel. So far, how we have solved such an issues is based on some support. Some old compiler, either they can be running in the newer versions, and how it run. We have iterated several process, and but we expect more future features coming from the software companies.
Very interesting. Thank you. Why are you using PSCAD versus Power Factory for your EMT studies, since Power Factory can do RMS and EMT on the same platform?
There are several pros and cons, I would say. The one of the reason why we run the PSCAD for EMT studies is that was somehow some historical reason, I would say. I think that was before I employed in Energinet. All the models since 2013 was based on the PSCAD model. So it's quite difficult to change such a model requirement, since if we would like to require all the model to be developed in the new environment, then actually it's also new challenges for us to cover all the cost and validations and so on. So based on that reasons, we developed the PSCAD based EMT environment. We know that the Power Factory also supports many different tools, the harmonics and RMS and the EMTs. Based on our experience, it's still quite not matured. Of course, for system level functions, Power Factory is really providing nicer features to get a system overview. But in a quality-wise of the EMT simulations, I think it's still not ready in our understanding and engineering experience.
Okay, very good, thank you. Another practical question. How many CPU cores do you need for PSCAD simulations of the entire network, including vendor IBR models? And do you use any clusters for parallel simulations?
We basically use Azure-based simulation server. You can imagine that the individual every single project require one single core to really optimize the simulation time. So as you can see in this slides, we are using currently 45 PNI for DK1 and around 60 for PNI is for the DK2. So we are currently using a 64 core hardware setup to really enable two different environment. So for the coming futures, like maybe next 5-10 years, if there are more vendor-specific IBR-based model coming, we believe that the hardware and all the parallel computing features will also evolve together. So we don't really concern about such situations.
Okay. When you observe an oscillation, what indicators require you to move towards an EMT simulation from an RMS simulation?
That is very good questions. Something I can answer is that based on such an events we have observed this DK2 and the DK1 simulations, only we see is that we were able to capture and the mimic the similar behavior in the EMT. So meaning that we cannot really evaluate for now which oscillation is really like a correct and accurate and precise to make decisions. But at least our understanding is that and based on our experience with the grid connection cases, typically some oscillation issues we have observed in the RMS environment, especially when the plant models are connected to very weak grid. There are some numerical issues, and some oscillation is coming from that numerical issues. Since there are some model reductions to deliver the RMS dynamic models, and basically, even if there are some oscillation, that was not really real oscillations like we have observed. That is our experience. So that if we see some oscillation in the RMS, I think that is somehow the indications that we need to think about the EMT domain instead to be sure that if that oscillation is realistic using some real code-based EMT based environment.
Okay. And went on time frames. At what time of the new project timeline do you consider assessing system stability?
For the development-wise, I'm not sure if I understand the question precisely.
Yeah, I think it's if you're doing a new project and it has a certain timeline, I don't know, 5-10 years, at what time do you consider assessing system stability? How early or how far into the project timeline?
We have now all the setup, and we have validated this setup using some of the cases have already introduced in this slides. As mentioned here, we need more cases and more validations throughout the coming project. So we think that our entire environment process will be more matured in the next 1-2 years.
Okay. Okay, thank you. All right, I'm looking at the clock here, and it's about the top of the hour, so I think we're going to need to wrap it up. And I want to thank Jun for this really informative webinar on the EMT analysis environment at Energinet. And as I mentioned earlier, an email will go out once the video file has been posted, and we'll answer the questions we didn't get to and get them posted as quickly as possible. We appreciate your participation, and if you would like to stay engaged, I would like to invite you to participate in the next round of ESIG webinars coming up in January. I'd also like to invite you to attend the ESIG Spring Technical Workshop in Tucson the last week of March. It'll be here before you know it. Further information on all of our webinars and events can be found on our website at esig.energy under events, and you're all invited to attend. Information on all the GPST webinars can also be found at globalpst.org. Jun, I want to thank you again for this very timely webinar and thank all of you for your engagement. We look forward to seeing you again in the near future. In the meantime, everyone, happy holidays, take care, stay safe, and thanks again for your participation.
Thank you. Bye.
Okay, thank you, Jun. Bye-bye.